Grace C. Brown, a co-author on the plasma study, said something that stuck with me. By understanding how stellar activity reshapes these signals, we can design searches matched to what actually arrives at Earth, not just what might be transmitted. That sentence is doing a lot of quiet work, because it means everything we've collected so far was filtered through assumptions that may have been wrong from the very first day. The data exists. The signals may be in it. We just need the right key. If this is bending your brain the way it bent mine, drop a comment. I want to know what you think the real reason is that we haven't confirmed contact. The technology gap? The signal distortion? Something else entirely? And the bigger question hiding behind this whole video, why the universe seems so empty in the first place? That's the Fermi paradox, and it deserves its own video. It's coming next. Because here's the thing that ties all of this together. We've spent 60 years asking, is anyone out there? And the honest answer, based on everything we now know, is that we're not sure we've ever been listening correctly. The answer might not require a new telescope pointed at a new star. It might require a new algorithm pointed at a hard drive that's been sitting in a lab for 20 years. The aliens may not be silent. We may just be deaf. And the most important shift happening in this field right now is that researchers have finally stopped asking, why haven't we heard anything? And started asking, what have we been getting wrong about how to listen? That's a completely different question, and it's the right one. If K2-18b ever does start talking, the listening tools will be sharp enough to notice, and sharp enough to tell a real voice apart from the noise we make ourselves. The search isn't over. It's just finally getting honest about what it might have missed. Subscribe so you're here when the next piece of this puzzle drops, because this story is moving fast. We already have a signal. We've had one for 60 years. The problem is we may have been filtering it out before we ever had a chance to hear it. Researchers now believe alien transmissions could have already washed over Earth, clean and clear when they left their home planet, then smeared into something unrecognizable by the time they reached our detectors. Not lost in the void between stars, scrambled right at the source before they even escaped their own solar system. And the filters we built to clean up the noise? They may have quietly deleted whatever was left. 3 separate problems, all confirmed or identified recently, point to the same uncomfortable conclusion. We're not necessarily alone. We may just be deaf. One of these problems is so fundamental, it calls into question 6 decades of assumptions. And one of them involves data we've already collected. Sitting on hard drives right now, waiting for someone to run the right algorithm over it, that's not science fiction. That's where the actual research is landing right now, and it changes everything about how we look for alien life. So here's the plan. First, the reason signals might be getting destroyed before they even leave the alien solar system. Then the blind spots baked into our own detection technology. And finally, the most unsettling one, the possibility that evidence of alien megastructures is already sitting in data we've collected, and we're only now figuring out how to read it. Stick around for that last one. It's the one that genuinely keeps astronomers up at night. But before any of that, we need to talk about the biggest radio scan ever pointed at one of the most promising planets we've ever found, and what the silence it returned actually means. Astronomers recently ran an unusually powerful radio survey of a planet called K2-18b, using 2 of the most powerful radio observatories on Earth, the Very Large Array in New Mexico and Meerkat in South Africa. Opposite sides of the planet, working the same target. Getting facilities of that scale coordinated on a single campaign almost never happens. Why this planet? K2-18b sits 124 light-years away in the constellation Leo, right inside its star's habitable zone. It's one of the top candidates for what scientists call a Hycean world, a thick, hydrogen-rich atmosphere wrapped around a global ocean of liquid water. The James Webb Telescope has already found carbon dioxide and methane in its atmosphere. As targets go, it's about as good as we've ever had. So what did we find? Nothing. Millions of potential signals came through during the observation window, and not one of them passed the filters. No artificial transmissions. Silence. Now most people hear that and think, well, no aliens there. But that's the wrong read. All it means is that nothing was broadcasting a narrowband radio signal we could detect at the moment we happened to be listening. If a civilization does exist there, it might simply be transmitting something our observatories can't pick up. And that distinction matters enormously because it leads straight into the first problem. Since the very beginning of CD, the search has focused on narrowband radio signals. There's a logic to it. They travel long distances, they need surprisingly little power, and they stand out sharply against the natural noise of space. Find the sharp, narrow spike. That's your alien. That's been the core assumption for 6 decades. The problem is that assumption may be completely wrong. Here's what a new study found. A narrowband signal leaves an alien planet exactly the way we'd hope. A clean, sharp spike. But then it has to pass through the plasma storm surrounding its own host star. All that turbulence, all those charged particles, they smear the signal. By the time it escapes into open space, that sharp spike has been broadened into a wide, flat smudge. Our detectors are looking for a spike. They get a smudge, and they throw it away. Vishal Gujjar, the SETI Institute astronomer who led the study, put it plainly. If a signal gets broadened by its own star's environment, it can slip below our detection thresholds even if it's there, which could explain some of the radio silence we've been staring at for decades. And here's the worst part. The stars most likely to scramble a signal this way are M dwarfs, which happen to make up about 75% of all the stars in the Milky Way. The most common star in the galaxy is also the one most likely to garble any message trying to leave it. The numbers are brutal. In roughly 30% of the star systems they modeled, the broadening was severe enough to destroy about 94% of a signal's peak strength, pushing it below anything our current searches would flag. Think about what that means. We haven't been failing to find aliens. We may have been using the wrong filter to look for them, and it gets better, or worse, depending on how you look at it. If searches are redesigned to account for this broadening effect, decades of old data suddenly become worth rechecking. Signals that already arrived, already got recorded, already got dismissed as noise. They might be sitting on hard drives right now, unread, waiting for the right algorithm. So that's problem 1. The signal gets scrambled on the way out. Now here's problem 2, and this one happens on our end. When the K2-18b team processed their data, they had to filter it hard. Radio telescopes drown in human noise. Satellites, cell towers, radar, all of it. Without aggressive filtering, you'd never see anything at all. But those filters have a cost. The most debatable choice they made, throwing out every signal with a signal-to-noise ratio below 10 or above 100. That's a reasonable way to kill false positives and instrument glitches. It's also a way to accidentally delete a real signal that just happens to be weak. Read that again. The very process of cleaning the data to look for aliens might be erasing the aliens from the data. And there's a timing problem too. One standard check is transit filtering. A real signal from the planet should vanish when the planet passes behind its star. Simple, elegant. Except during this survey window, no transit happened, so the check couldn't be used, which tells you something uncomfortable. When you look matters as much as how you look. Catch a planet at the wrong point in its orbit, and even a genuine signal can get cut. And underneath all of it sits a third bigger assumption. This entire approach assumes that an advanced civilization would communicate roughly the way we do, that beings possibly thousands of years ahead of us would use technology we invented in the 1950s. Maybe, or maybe they're communicating in ways we don't have words for yet, let alone detectors. Now here's where it gets really interesting. This is the one I mentioned at the start, the one that keeps researchers up at night. While one group of astronomers has been listening for radio signals, another group has been hunting for something far more dramatic. Dyson spheres. The idea is simple and enormous at the same time. A civilization that outgrows its planet's energy supply, builds a structure around its entire star, and harvests the star's power directly. You'd never hear a message from something like that, but you would see something strange from the outside. A star giving off way too much infrared heat for its size. Not a signal, not a greeting, just the waste heat of a machine the size of a solar system. In 2024, a search called Project Hephaestus went looking for exactly that signature. They screened roughly 5 million stars using data from 3 different sky surveys. 5 million stars. 7 of them couldn't be explained. 7 stars with an infrared excess that didn't match anything natural. And these weren't easy to wave away. The temperatures were too high, and the brightness patterns were wrong for ordinary dust disks, which are extremely rare around these kinds of stars to begin with. Now, before anyone gets carried away, researchers have spent the time since trying to knock these candidates down, which is exactly what good science does. And some of them are probably contamination. At least 2 of the 7 turned out to have infrared bright background galaxies sitting almost directly behind them, close enough to pollute the measurement. The real culprit is the limited resolution of our current infrared sky maps. When you match up images from different telescopes, distant objects can blur together and fool you. But here's why that's encouraging rather than deflating. We found 7 candidates out of 5 million stars. The screening process worked, and now telescopes planned for the 2030s will have the resolution to settle the question properly. We're not at the end of this search. We're at the beginning of finally being able to do it right, and that's the thread running through everything in this video. The K2-18b scan didn't fail. It built a framework that will shape how these searches run for years. The plasma study didn't just find a problem, it handed researchers a way to reprocess decades of old data. The Dyson sphere hunt didn't collapse. It exposed exactly which tools we need to build next.